Assalamualaikum warahmatullahi wabarakatuh and very good day. So we continue on the DC motor. So this is the first DC motor type that will be discussed, which is the shunt connected DC motor. So shunt connected meaning that the field circuit and also the armature circuit are connected in parallel as shown in this figure. Okay, and as you can as mentioned in this slide, uh, I just want to highlight that the field circuit which is here is represent the winding at the stator, while the armature circuit represent the winding at the rotor part. And this field circuit is actually not a main circuit. It is only used to produce flux. Okay, so to control the flux, you need to control the IF, okay, by either uh, adjusting the value of RF or just put another resistor which is uh, adjustable. Okay, and as you can see here, IL here is the I total, which is the I source, which is equal to IF plus IA, and this is the armature circuit contains RA and also back EMF. And I would like also to remind you, okay, that for the field circuit, you can all for a steady state condition, you can always ignore the inductor because in a steady state where there is no change of current, so the voltage drop across the inductor is almost zero. And this is the power flow for the shunt DC motor. So this is the power input, which is you can calculate by using VT multiplied with the I line or I source. Okay, and we have some losses, which is losses at the field circuit, and then we have losses at the armature circuit. So the power developed from the motor, so from the motor, which is you can calculate by using electrical parameters IAEA, or you can also use mechanical parameters to calculate. Okay, and then if you minus the rotational loss, which is sometimes is quite difficult to calculate, okay, you can get your actual output power. So as you can see, the torque output and the torque developed before the rotational loss is different, but the speed is assumed equals. So that is for the shunt DC motor. And this is the torque speed characteristic of the shunt DC motor. So to obtain the torque speed characteristic, you can actually start from the armature circuit itself. So applying Kirchhoff voltage law to the equivalent circuit shown in figure 16.16, which is the shunt DC motor, we can obtain that the voltage terminal, okay, which is this one, VT here, is equals to the voltage drop across the armature resistance plus the back EMF. Okay, and we know that IA, which is from the equation of torque, which is T is equal to K flux IA. Okay, when we rearrange this to this equation, okay, and then using EA is equal to K flux omega M. So we substitute both IA and EA into this equation. So we will have the equation, which is a linear equation that use torque and as the main title and the speed as your variable. So this is a linear equation, which is you can show which is equal to y is equal to mx plus c. So y is your torque while x is your speed. Okay, and c is actually the cross at the y-axis. So if you plot this, okay, if you plot this, you will have a negative slope, okay, with a cross at this position and cross at this position. Okay, this cross at this position at axis plot is actually we call this is the speed, which is the no load speed where the torque is 0. So this is where the rotation of the motor where while there is no load connected to the motor. Okay, and at this point, this is what we call the stall torque. So stall torque meaning that the motor is not rotating. So the value of the torque that if you want the motor to be not removable, not it's actually not rotation. There is no rotation. Okay, you avoid the rotation. So or you want to counter the rotation of the motor. So you need to connect the motor with a torque which is has a value of a stall torque, which is you can calculate by using K flux over RA VT. Okay. And the second circuit that we will discuss is actually separately excited DC motor. So as name imposed here, separately excited meaning that the field circuit here and also your armature circuit here has separate DC sources, which is the field circuit is supplied by a separate source VF, and the armature circuit is supplied by another separate source, which is VT. Okay, so the flux is generated using separate source, which is IF here. Using the field circuit, the flux is proportional with the IF. And since it is separated, meaning that the armature and field circuit is independent to each other. Okay, it's actually contrary to the shunt connected, where as you can see, it is connected in parallel. So if IF is increased, so IA will reduce. So the IF will have effect on the armature current. But for the separately excited DC motor, the effect of IF and IA are independent. Okay, so based on the equation of the armature circuit, okay, we can derive the torque speed characteristic, which is the same with shunt DC motor, meaning that the separately excited DC motor performance is, we can say, is equivalent to the shunt DC motor. And this is example 16.4, which is will be discussed in during our class. Okay, the last one is the series connected DC motor. Okay, so as you can see here, the field circuit and armature circuit is actually connected in series, where IA right now is equals to your I field. And we use this equation, which is flux. We know that flux is always proportional with IF. So we, to actually relate IF, so we equals to a constant KF IF, where KF is a constant that depends on the number of field winding, the geometry of magnetic circuit, and the pH characteristic of the iron. And because IA is equal to IF, so we can rewrite the equation of flux is equal to KFIA and substitute flux in equation of the back EMF and also torque, we will obtain this equation. And finally, when we apply Kirchhoff voltage law to the equivalent circuit, which is VT is equal to RFIA plus RAIA plus EA, and then substitute this EA to this and IA to these two, so we will obtain the torque speed equations. Okay, so as you can see, this equation 16.34 shows the torque speed characteristic equation, which is this one is a quadratic equations, meaning that the plot is actually somehow non-linear, which is a quadratic equation here. Okay, so based on the equations of 16.34, where when the torque is zero, when you substitute torque is zero, the speed is equals to infinity, meaning that the motor will rotate at very high speed. This is the theory, but in practical, we need to consider rotational losses, okay, during at the motor. So usually when torque is equal to zero, there is a speed of the motor. The motor will not go very high, okay. So however, in some cases, the no load speed can become very large enough to be very dangerous. So it is important to have protection device that remove electrical power to a series machine when load becomes disconnected. So it's very difficult. If you want to, for this series connected DC motor, make sure when you want to disconnect your load, make sure that maybe you reduce the voltage input and so on, so that the speed is not at very high speed. Okay, and as you can see from this characteristic also, for the very low speed here, okay, the current IF and IA will become very large, and therefore the torque is also very large, okay, based on this equation. Okay, so if the speed is very small, you can see that the torque is actually become very high. So this is example 60.5, and this will be discussed during our class. Okay, so I think that's all for this video. So next video will be discussing on the speed, how we can control the speed of the DC motor.